Postgres user group. We are Lætitia abroad from Enterprise DB, presenting a very challenging task, chasing unicorns. I think the presentation is full of unicorns, zero data loss, and 99.999% availability. So yes, very interesting talk. The mic is yours, Lætitia. So cool. Thank you.
Okay, thanks for the introduction, Federico. So we will speak about data loss and availability, how it's frustrating because we can't have both, but how we could try to get something closer to both, because of course we can't have both. So first, who am I? I'm Lætitia Avro, and you can find my blog, mydbnotebook.org. Why do I speak about my blog on a conf talk? Because my slides are pretty clean without any words, and I know that some people are more comfortable when slides are full with words, so they can keep up easily. So if you, in that case, or if later you want to recall what we said, even though it's a recording, you can go to mydbnotebook.org. You will find a tab called Conf Talk, and then you will have a direct link to the slides, but it's not the exact same slides. It's slides with words. So it's easier to be seen and to share with colleagues that didn't see the Conf Talk. So if you need words, please be my guest and go fetch a slide to be able to follow. Another thing about me, you can follow me on Twitter. And I try to keep my Twitter account professional, but it's internet and you will find some cute kitten and things like that. I'm sorry about that. About Postgres, who am I? I'm a Postgres consultant for Enterprise DB, and I'm Postgres Women co-founder, and I was elected recently as the treasurer in the board of PostgreSQL Europe Association. And today we will speak about chasing unicorns. Of course, we know unicorns does not exist. It doesn't mean that we don't want to see one. And it's exactly the same thing about data loss and 5 nines. So let's first speak about, we will speak about data loss and downtime, and we will also speak about some mathematical theorems that maybe you know about, which are the CAP theorem and the PACELC theorems. And after having stated that it's, of course, impossible to have 5 nines and no data loss, we will find what we can achieve with some kind of blueprints architecture for Postgres. So first, let's say it, there is no such thing as data loss in the universe. So if you want to explain it, it's really simple. Most of our computers are on Earth, and if Earth explodes, then there will be no computer, and you may have so many backups that you want. There is no way you can achieve zero data loss in case of Earth explodes. Okay, that's extreme, but it's just to show you that when a mathematician says zero data loss or an informatician says zero data loss, it actually means zero. Maybe when you said you wanted zero data loss, you didn't mean zero. And that's what it's all about. I had a customer that said, who said that he wanted zero data loss. And I speak with him about it, and I found out that zero meant that he was able to lose something like 1 hour of transaction a day. That's a lot of loss. But to him, it was kind of zero because for his business, this was zero. So the first thing you need to know, if you're a consultant in database, you need to be able to speak with other people. You need to be able to ask the right question to understand what 0 means to them. Another thing is downtime, because of course people say they want 0 downtime, meaning 100% of availability, which is very difficult to achieve with an RDBMS, and we'll see after why. So it means 0 microseconds, 0 of failure daily, weekly, yearly. That's nearly impossible, because failure always happens. We know that. We're in IT. We know it always fails, and that's what makes our days so different and interesting. What about 5 nines? What does it mean? So 5 nines means that we can have less than 1 second a day of downtime. It means 6 seconds a week of downtime, and less than 5.5 minutes of downtime yearly. That's not a lot, because in this time you need to be able to create your maintenance task, and you have to be able to manage incidents and what was not foreseen. So 5 nines, that's difficult to achieve. What about 4 nines? 4 nines is more reasonable. It means less than 9 seconds of downtime a day, around 1 minute weekly, and 2 days yearly. That's still difficult to achieve, but it's more reasonable than 5 nines. What about if I say I have a maintenance window of 2 hours by night? So it means that this, if you take this time into account in your failure time, it means 2 hours a day, it means 14 hours weekly, and 30 days yearly. So you're okay with routine maintenance, it will work. Your problem here is, what if it fails outside of your maintenance window? And if you have some kind of application that works only during the day, we can imagine something like some kind of an internal application for a company that works only during the day. It means something around 12 hours a day of failure time allowed, and 3.5 days weekly, and more than 180 days yearly. But what happens most of the time, it's not that you can use this failure time allowed during the night and report it during the day on your downtime statistics. It doesn't work that way. What you will say will be more like, I want 5 nines during day. You can have any failure you want during night. And in that case, it's worse that 5 nines, 7 days a week and 24 hours a day, because in that case, it means that you're allowed less than 0.4 seconds a day, less than 3 seconds a week, and less than 1.5 minutes a year. That's even not enough for maintenance routine. But that's what happens most of the time. Another thing you need to have in mind when you're trying to describe how much downtime you can have and so on is databases are rarely the only thing in your architecture. You have a lot of other components here, and each one of them can fail. So your database, for example, won't be able to work if the hardware it's sitting on fails. So if your hardware is not capable of the 5 nines, your database won't be capable of the 5 nines. And on top of the hardware, you have the OS. the operating system, so it's the same thing. If it's not 5 nines capable, you won't be able to achieve 5 nines with your database. It's worst when you're using virtual hosts and containers because you have other layers that, and each of these layers can fail. And of course, there are other components in your architecture because you have an application that also relies on an operating system, on hardware, and you have network between them. And then you will have another network. Sometimes it's even the internet with a client on top of that. So just it's good to size your database and your hardware and everything so it can support downtime and it will match your downtime goal. But be sure that each one of the components in your whole architecture is able to support your downtime goal. For the rest of the presentation, I'll assume that all the other components are okay and that the database is the weakest link. It's just an assumption. It doesn't mean that it's true every time because most of the time it's not true. You really need to be very careful about that. So let's say what math can do to help us. Well, actually, math can do what math can do for us is frustrating because math can't help. What math said was when you're designing a distributed web services, there are 3 properties that are commonly desired: consistency, availability, and partition tolerance. And what math tells us is it's impossible to achieve all 3. So that's kind of frustrating, but it's the real world. Meaning when you have consistency and availability, you won't be able to have perfect network partitioning. When you have a network partition and availability, you won't be able to achieve perfect consistency. And if you have consistency and network partitioning, there's no way you can achieve perfect availability. That's the problem here. But what does consistency mean? Consistency means that each node will see the last committed version of the data. There is no way you can retrieve an ancient version of the data, an obsolete version of the data. Availability, it's really simple. It means that the system will always answer something different than an error message. So it can answer anything but an error message. And network partitioning is the ability of the network to be allowed to lose arbitrarily many messages sent from one node to another without altering the system answers. So if we put that together with the CAP theorem, it says that we can't have all 3 of them. But I like to say the CAP theorem as a rubber band about 3 poles. The rubber band is too short to be able to wrap around the 3 poles. But what you can do is wrap your rubber band about 2 poles and stretch to not meet the 3rd pole. You can't, it's too short, but you can stretch to be as close as you want from the 3rd pole. That's how I imagine the CAP theorem. I heard a lot of people saying that RDBMS are CR, meaning that they favor consistency and availability and not network partitioning. So let's talk a little about that because I disagree with that. RDBMS are sometimes CR, sometimes AP and sometimes CP. They are not always CA. So here's how I see it. I will use the B metaphor because I don't like using the master-slave denomination. So queen is the master, the primary node. It's the one you can write in. There are two other kind of nodes. A princess is already there to take the place of the queen in case of the queen fails. And the worker is there just to be able to serve read queries. So here we are in a standalone case. So we have only one cluster. It's a queen. And in that case, it's pretty simple because as there is no network, there is no network partitioning. And that's why we can say that this case, we are CA, consistency and availability. In the second case, we have a queen and a worker that's asynchronous. If it's a worker, it means that we are able to retrieve queries, read queries from it. But as it's an asynchronous streaming replication, or a logical replication, or whatever, it doesn't matter. Here, what matters is it's asynchronous, meaning that there is some risk that when we read data from the worker, it's not the last committed value of the data. In that case, it means that we are AP, availability and network partitioning. It means that in case of a failure of the queen, the worker will still be able to serve read queries. Maybe it won't be the last version of the data. So we will drop consistency on that one. It doesn't mean there will always be obsolete data. Sometimes it will be accurate data, but we can't validate, we can certify that it's the last value of the data that we read from the worker. Let's talk about the case of multi-primary. So we have two queens here. And in that case, in Postgres technology, there is no way we can achieve that with synchronous replication. So it's always asynchronous. And so wherever we read, we have a risk of not reading the last version of data. So we're AP here, meaning that we have availability, we have partition, network partitioning, but we are not sure to have achieved consistency. There is another case where we have a princess that's synchronous. We could have a worker synchronous, but I don't like that case because in my mind, you have to choose what role you want to give to your instance. Does it need to be a princess? Meaning, does it need to be ready in case of the queen fails? Or does it need to give answers to read queries? In case of a synchronous replication, what's important here is that the princess need to acknowledge each commit if that occurs in the queen. So if the princess fails, there will be no write in the queen. So we will drop availability to preserve consistency in case of network partitioning. So we will be in the CP case. But we can go further because the CAP theorem is not the only one that tried to help us, because it's frustrating when a mathematics theorem just tells us that it's not possible what we're trying to achieve. And it goes further. So the PACELC theorem is that it states that in case of network partitioning, in a distributed computer system, one has to choose between availability and consistency. That's exactly the CAP theorem. But else, even when the system is running normally, in the absence of partition, one has to choose between latency and consistency. Meaning that there might be a way to answer queries quicker, but if we took that path, maybe we will take down consistency by doing so. First, I think we need to define what latency is. Latency is the amount of time the system needs to answer when it's smaller than a request timeout, of course, because a request timeout is an availability problem. When the author of this theorem wrote the article about that, he asked himself the question, what's latency? And he found a paper from Amazon. Amazon has this problem that when there was too much latency on their website, people weren't buying. And so they made a study to quantify what was the amount of latency that made people stop buying. And they found out that if charging the basket took more than 250 milliseconds, people didn't buy items. So that's quite extreme, but 1/4 of a second is enough for the human brain to see it as latency. Some systems are less critical and latency can be more than that. But just so you know that in a web application, most of the time, we will consider that 1/4 of a second is enough to be considered as latency. So what can we do about that? So first, you have to ask yourself, what do you want? When you have someone telling you that they want zero data loss, they want zero downtime, you have to quantify what this zero means. That zero means that you can afford to lose 6 megabytes of transactions. Does zero data loss means that you can afford to lose 1 second of transactions? Downtime, what does it mean? Zero downtime, is 1 hour of downtime acceptable? Is it not? Etc. Why do we have to do that? Because we will design different architecture depending on the answer we will have. And why do we need to design differently the things? Because we don't want to create something too complex. We want something simple, because when it's simple, you can manage it easily and you can upgrade it easily and it's cheaper and so on. If you create something really complicated when it's not needed, it will just be costly for nothing. So you really need to answer this question first. In the blueprints I created, these are minimal configuration. You can always add more standbys, more princesses, more workers in able to achieve what you want to achieve. And still the same thing. You can create a wonderful architecture with your database, and your database will be able to reach 5 nines. But if it's created on top of hardware who can't achieve 5 nines, or if it's on a network that is really weak, it won't work, because you really need to bear in mind that you really need to create the whole architecture as a whole, not only the database thing. And that's very difficult because database is a pretty strange area for a lot of people. So when you want to achieve near zero data loss, and I emphasize the near zero, what you can do is create this kind of architecture when you will have a queen, you will have a synchronous princess, and your application will send read-write query over the queen. I'm talking about data loss. I'm not talking about downtime here. Of course, if the princess is down, you won't be able to write in the queen. And in the queen is down, you will be able to read, you won't be able to read from the princess because it wasn't designed to be able to answer read queries. So to me, it means that we dropped the availability thing and to achieve consistency and some kind of partition network. What's important here is once data are committed on queens, they are committed on princess, and then the application got the message saying that the data are on disk and there's no way this data can be lost. That's durability, and it's really important. That's why I say we can achieve near zero data loss with that kind of architecture. Just one thing is, as the queen needs to send the data to princess before being able to answer the application to say that the data has been committed, you need queen and princess to be really close or on a really fast network, because you don't want to add network lag on top of it. If you have a system that is so slow that you will end up with timeout each time, it won't be available. So that's not what you want to achieve. Most of the time, what we advise our customer is to put the princess in the same data center than the queen and on the same network, so that the lag will be around 100 and 200 milliseconds. When I mean lag, it's just the time to go to the princess and go back and then be able to set the applications that the data are committed. So in this case, we are able to achieve a CP case of the CAP theorem. What about the 5.9 availability architecture? If you want a 5 node availability, you can't rely on one node only. And the thing is, you will be, if you want several nodes that are capable of reading and writing, you will have to go through logical replication. There are several software that can achieve multi-queen configuration. There's just one thing you need to know is when you will achieve some kind of architecture that way, you will have to ask yourself, what if there is a conflict in data? What if the application wants to change the same data at the same time between queen A and queen B? Which one will be the winner? How can I solve those kind of conflicts? This kind of architecture is really complex and will cost a lot in maintenance time and in conflict resolution. But I think we can say that in this case, we have achieved to have availability and partition and network partitioning, but in the cost of slowing down consistency, because as it's a logical replication, it's asynchronous, and there's no way we can be sure that when we retrieve data from queen B, there is not more recent data on Queen E. There's no way we can be sure that it's really the last version of data we're reading. So sometimes you have to compromise. You have to be able to find trade-offs. And what's very common here is to use a system with 3 nodes. Of course, you can customize it, adding other nodes to create something you will find maybe better. What it can achieve less availability. It will achieve less availability than the 5 nines, but on the other side, you will have more data consistency, as that's for some application very important. So we have a queen and we have 2 princesses, but on synchronous replication. But what we will say is we just need 1 princess to answer to be able to go back to the application and say, okay, the data are committed. So in that case, only one of the fastest of the princess we answer, meaning that we can have 1 princess in the same data center on the same network, but we can have another one on another data center. It will take more time to answer, but it just means that in case of the princess R fails, we will have it will take more time to have the answer for Princess B, but we will still have an answer. And so we won't have no availability of the queen in case of a failure of a princess. So to me, it means that we have achieved consistency and network partitioning, but we stretch over availability to have better availability than if we had only 1 princess. So what you need to know is, and I really emphasize about that, and it's really important, it's database is not the single point of failure. There are a lot of them, and you really need to be very to take care of that, because it's very important. All our IT systems are based on hardware, and hardware fails all the time. So you really need to be sure that in case of hardware failure or other component failure, that you will have a way to keep going, or that the downtime will be acceptable. The second one, which is really important to me, is you are probably not Google. So it doesn't, it's not because Google has this whole amazing architecture and infrastructure, it doesn't mean you have to create the exact same thing. I would say that you don't need all that. The simpler your architecture is, the simpler, the easier it will be to maintain, and the less costly it will be. You really need to quantify your manageable data loss and your manageable downtime. That's really important. And it's still amazing for me when I go to a customer and I find out that they have no answer to these questions. And so I try to find the answer with them, and we discuss about it. But the thing is, it's never written in a document before I come into their company. It's never written. How much data loss can I have? How much downtime can I have? But it's critical for the company to know how much data loss I will have, how much downtime I can afford. It's really important, because if you don't have this, you can create the simplest architecture. So you will create something by guessing what's best, but you can't design good things just by guessing what could be the best. And I'd like to close this with a quote from my friend Gershwin. She said that unicorns are more real than zero data loss and 5/9 availability. She said that when I was trying to explain that to a customer, and that's how she found a way to explain it to non-IT people. And I really thank her for that. And I have finished. If you have any question, I don't know if you can ask question on the Meet chat, or if you can.
There's been a little problem about this stream.
Yes.
I didn't do RTFM about the Google manual, so unfortunately, just the last 30 minutes have been streamed. I had to reroute the connection through OBS and then over YouTube to the old Postgres user group in Brighton meetup. Has been, you are told that I've been through a quite interesting, frantic moment. So I think but yes, has been recorded, so I will upload into on YouTube anyway. Let me check onto the Telegram channel at this point.
Yeah.
Let's see if anybody have any question. Sorry about that. There's been
it's the first one. It happens.
Well, the Murphy's law.
Yeah, of course.
By the way, 5 minutes before starting this meeting, I had the call for a parcel, getting my new gaming chair, 25 kilo to push up over 2 flights of stairs. So yes, it's been an interesting moment, complete demonstration of the Murphy's law.
Yeah.
Let's see if we have anything. Yes, Nick is asking if you are logging about that.
I'm not saying about Murphy's law. It's always that way.
So yeah, in the meanwhile, I've also updated the community page. People are looking at the community page instead of you. So yeah, that will be an interesting stream and recording anyway. So let me let's see if there's any real question about that. Well, at least we have fun.
Yeah, sure.
By the way, I got the same chair you have. Still need to be assembled. Okay.
It's really easy.
But I think the next time we will use Jitsi.
Yeah.
Is a better thing.
Sure. Whatever.
I used you as a guinea pig. Sorry about that.
Don't worry. We needed to try it.
Yeah, we learn for our failures. Okay, Nick is asking about Patroni and related software. Don't you get at least near the 5 nines using Patroni?
I don't think so, because there's still a lag when you have to switch over or to fail over. You can't fail over each time you have any network shortage. So you need to have some kind of timeout about that. And what we saw is if you want to achieve 5 nines, it means that you will have less than 5 minutes downtime during a year. 5 minutes is typically the kind of timeout you get to be able to say, okay, it's not a network shortage, it's really a downtime problem, and there you can fail over. So I think that you can't use Patroni for that. The best way to achieve 5 nines is really using multi-queen system.
Multi-queuing system, you mean something like Kafka? For
there are several things in Postgres world, but I think like BDR or like XDB or things like that. So it's built over PG logical or logical replication.
Okay, so trying to keep the data synchronized as much as possible.
Yes.
Yeah. And that's my question. Continuing about this thing, what about setting up synchronous replicas for having the absolute certain you have data in sync?
When you add synchronous replication, you will add some lag in your queen system. And in system, when you want to achieve 5 nines, these are quite a critic system where lags is not allowed.
Mm-hmm. Okay, so it's a trade-off not to get. Okay.
Yeah.
Thank you very much.
You're welcome.
There's a slight lag on the stream. I think it's about 30 seconds, but that's normal because it has to get ingested by YouTube. So
okay.
They got the answer anyway. Oh, we have 7 viewers, which is good considering the the disaster. It looks like there are no other questions. So yeah, sorry about that. Thank you very much for. Say the hear only you. Okay, another interesting thing.
Yeah.
That's interesting. Okay, they hear just you.
Yeah.
Okay. But I think we are recording anyway the my voice because it's okay. Probably I forgot to add the something else into the OBS stream. So I'm just recording you, but not recording me. So that's it.
Oh,
so, yeah. It's good that at least you are being streamed and listened. So that's okay. I'm not important. So okay, let's close this disastrous first time. Thank you very much for
You're welcome.
your talk. I will upload and share the talk as soon as it is encoded and available for download.
Okay, great.
Cool. Thank you very much. Stopping the recording now. Start